All right, get ready to stretch those brain cells because today we're going deep, really deep into string theory. You guys sent in a ton of stuff on this one. Articles, research papers, even some of your own notes. Clearly, you're ready to move past string theory 101, so we're going straight to the big question. String theory, and could it really be the key to like the ultimate mysteries of the universe? Let's find out.
It's a question that's had physicists and philosophers scratching their heads for, well, a very long time. What are the fundamental, the absolute most basic building blocks of, well, everything? And how do those tiny pieces all come together to create the universe we see and experience?
It's like we're always trying to zoom in further and further, right?
Yeah.
Trying to find the smallest ingredient in the cosmic recipe. We see mountains, rivers, trees. We dig deeper and find cells, molecules, atoms. But even those are made of even tinier things.
Exactly. And that's where we get down to these things called elementary particles, the tiniest bits of matter we've discovered. But, and here's the catch, they're so small that we can't actually see them in the normal way we think about seeing.
Wait. How can you not see something? It's either there or it isn't, right?
Well, in the quantum world, things get a little fuzzy, a little uncertain. Think about it this way. Seeing is really about light bouncing off of something and then hitting our eyes.
Right, makes sense.
But with particles this small, the light waves we normally use to see, they're just way too big. Like clumsy giants trying to examine something incredibly delicate.
So it's like trying to use a basketball to, I don't know, feel the texture of a grain of sand.
Yeah, perfect analogy. And to make things even weirder, when you do try to see these particles, you have to use higher energy light, and that actually ends up changing them. It's like the observer is poking the thing they're trying to observe.
It's like just by looking at something at that level, you make it do a little dance.
Kinda. It's wild, right?
Really wild.
Yeah.
But how do scientists even work with something that's so elusive? It seems impossible.
Well, that brings us to one of the most important, if not the most important, ideas in all of quantum physics, the Heisenberg uncertainty principle. It basically says you can't perfectly know both the position and the momentum of a particle at the same time.
Meaning?
Meaning the more you try to nail down one, the fuzzier the other one gets.
So there's like this inherent fuzziness to reality at the smallest scales.
Exactly. And that's a pretty profound idea, right?
It really is. Did that mean we're doomed to never really pin down what these particles are actually doing?
Not quite. Physicists are a clever bunch. They came up with this brilliant workaround. We call it the point particle.
Point particle? Okay, I'm intrigued.
It's a simplification. Instead of trying to track down every possible detail of a particle's existence, physicists decided to treat them as if they were just points in space. Points with a specific set of properties like mass and charge.
I see. So it's like saying, hey, we can't know everything about this tiny thing, but we can know its key characteristics and use that to make predictions about how it'll behave.
Exactly. And the amazing thing is, this approach has been ridiculously successful. It led to the development of quantum field theory, or QFT. It explains the behavior of particles and the forces between them with incredible accuracy. It's the foundation of the standard model of particle physics. It's explained so much about the universe, except for one really stubborn outlier.
Oh, there's something this incredibly powerful theory can't explain. Now I'm really interested. Tell me more.
The troublemaker is, of course, gravity. You know, that force that keeps our feet on the ground, the planets in orbit. It's totally different from all the other fundamental forces.
You're telling me there's something QFT, this incredibly powerful theory, can't explain. Okay, I'm all ears because I have a feeling this is where things get really interesting.
You got that right. Okay, so you see, in quantum mechanics, the other forces, electromagnetism, the strong and weak nuclear forces, they're all carried by particles. But Einstein's theory of general relativity, it paints a totally different picture for gravity. It says it's not really a force, not in the traditional sense anyway. It's more like a curvature, a bending of space-time itself.
Okay, hold on. Curvature of space-time. I'm going to need you to unpack that a little.
All right, so imagine space-time like a giant trampoline. If you put a bowling ball on it, what happens?
It sinks down, makes a dip.
Right. And that's kind of what massive objects like planets and stars do to space-time. They create these curves, these dips, and that's what we experience as gravity.
So it's not that the Earth is pulling me down with some invisible force. It's that I'm, following the curve of space-time created by the Earth's mass.
You got it. And that's where the conflict comes in. In the quantum world, everything is about particles interacting with each other through forces. Forces that are carried by, well, more particles. But gravity, according to Einstein, is all about the geometry of space-time itself.
So we've got these two incredibly successful theories. quantum mechanics and general relativity, but they seem to be speaking totally different languages when it comes to gravity.
Exactly. It's like trying to fit a square peg into a round hole.
That's got to be a major headache for physicists.
It is. And that's precisely where string theory comes in. It offers this tantalizing possibility of bridging the gap.
Okay, string theory. You've mentioned it a few times now, and I've got to say, I'm hooked. What is it about this theory that makes it a potential peacemaker between these two giants of physics?
The core idea is actually pretty simple, at least at first glance. What if, instead of these point-like particles being the most fundamental building blocks of the universe, it's actually tiny vibrating strings?
Vibrating strings. That's not what I was expecting. Okay,
Okay.
I need you to paint me a picture here. What do these strings look like, and how do they relate to all the particles we've been talking about?
Imagine a guitar string, right?
Okay, I'm with you.
When you pluck it, it vibrates at a specific frequency, creates a particular note. Well, string theory says it's kind of similar, except instead of musical notes, these tiny minuscule strings vibrating at different frequencies, they give rise to different particles.
So an electron would be like one note on the string,
Mm-hmm.
and a quark would be another note.
Exactly. And here's where things get really, really mind-blowing. One of the possible notes that these strings can vibrate at, it corresponds to the graviton, the theoretical particle that carries the force of gravity.
Oh, hold on. So string theory actually has a built-in way to explain gravity as a particle.
Mm-hmm.
Just like the other forces in quantum mechanics, that's huge.
It is, and that's exactly why string theory caused such a stir when it was first proposed, because it had the potential to be the holy grail of physics,
Yeah.
a theory of everything, a theory that could finally unify all the forces and all the particles in the universe under this one elegant framework.
I can see why physicists were so excited. It's like solving the ultimate puzzle. But you did say there were some strings attached, right? Yeah. What are the challenges that come with this theory?
Well, for one thing, to make the math of string theory work, you need more than just the three spatial dimensions we experience, length, width, and height, and the one dimension of time. String theory needs, get this, 10 dimensions.
10 dimensions. Okay, wait a minute. Where are these extra dimensions? I'm only experiencing 4.
That's the million-dollar question, right? One idea is that they're curled up incredibly tightly, so tiny that we can't observe them.
So it's like each point in our familiar 3D space actually contains an entire multidimensional universe, all folded up in there like some kind of, I don't know, cosmic origami.
It's definitely mind-bending stuff. And there's another big hurdle. String theory, elegant as it is, hasn't yet made any testable predictions. Predictions that have actually been verified through experiments.
So it's a beautiful theory, but we don't have concrete proof that it actually describes our universe. Does that mean it's all just a mathematical curiosity?
Not necessarily. Remember, we started by talking about how humans use stories to make sense of the universe, right? Well, even if string theory isn't a perfectly accurate representation of reality, the math and the concepts that it uses, they can still be incredibly valuable.
I mean, that makes sense. It's like, even if the story isn't literally true, it can still give us new ideas, new ways of thinking about the universe.
Exactly. It's like, imagine you're an engineer, right? And you're trying to design a skyscraper, but all you have are blueprints for a treehouse.
Okay, I like where this is going.
The skyscraper is obviously way more complex, but studying that treehouse, it can still teach you valuable lessons of structure, materials, adapting to the environment.
Ah, I get it. So string theory is like our treehouse blueprint.
Yeah,
Even if it doesn't give us the complete picture of the universe, it can still offer some clues about how gravity might work at the quantum level.
precisely. And it gives us these powerful mathematical tools to explore these really strange places in physics, places where quantum mechanics and general relativity just clash, like black holes.
Oh, yeah. Black holes. I remember reading that string theory has been used to study the, what was it called? The information paradox.
Yeah, the information paradox, it's a real head-scratcher. Basically, quantum mechanics says that information can never be truly destroyed.
Right.
But if you toss a book into a black hole, it seems like all the information in that book, the words, the stories, the ink on the pages, it's all gone.
Which is a problem because it violates one of the fundamental principles of quantum mechanics.
Exactly. It's a big problem.
So how does string theory help us out here?
Well, string theory suggests that black holes might not be the information-destroying monsters we thought they were. Maybe they act more like, I don't know, cosmic hard drives, storing information in some way that we just don't understand yet.
So string theory could potentially reconcile these seemingly conflicting laws of physics, even in the crazy environment of a black hole.
That's the hope. And that's what makes string theory so fascinating. Even without direct experimental evidence, it's pushing us to think in new ways, to explore new possibilities.
It's asking the right questions, making us look deeper and imagine things that seemed impossible before.
Exactly.
Well, I think we've given our listeners a lot to think about today. From tiny vibrating strings to black holes and the vastness of the cosmos, it's clear there's still so much we don't know.
Absolutely.
But that's part of the beauty of it all, right? It's the mystery that keeps us exploring and asking questions.
Couldn't have said it better myself.
To everyone listening out there, we'll leave you with this. If string theory can make us question the very fabric of reality, imagine what other seemingly impossible ideas are out there, waiting to be discovered. Keep exploring, keep asking those tough questions, and never lose that sense of wonder. Who knows what incredible stories the universe has yet to tell us?